Hello, in this video we're going to talk about the least squares regression equation. In the sense, we're talking about bivariate data, and if it follows a linear relationship, then how can we describe that relationship by putting a line to it? So how do we do that? Well, I would like to draw an image. So I've drawn a little scatter plot here. And how would we put a line that describes this little bivariate data set? Now I might draw a line, and I'm doing my best here. How do I know, if that's the line, how do I know that it's the best line? Well, there are certain criteria that have to be met. What we look at are these things called residuals. So imagine this little pink distance, which is the distance from an observation to the line. And every single one of these has one of these little distances. These are called residuals. So a residual is the distance. Now it's a vertical distance. So this is a change in y values. And it's between the observed y value and I'm going to call it the predicted y value. The observed y is from the data, and the predicted y is from the line. So the best fit line is the one in which all of these little pink residuals are as small as possible. Actually, I've fibbed a little bit there. The best fit line is actually the one in which the squared residuals, when you add them all up, are as small as possible. You can maybe imagine, what if I had put a line to this data that was definitely not a good line, like this one. Boop. You would still have all these residuals, but they would all be so much bigger, right? So you can tell that that would not be the best line. And I'm going to actually delete all of those. The line that accomplishes this task is called the least squares regression line. And so the word least squares, right, because these residuals are squared, and we want the sum of these residuals to be as small as possible, or least. This least squares regression line, it's a line, right? So it follows the y equals mx plus b format. But usually when we are creating this line, so we have a number for the slope and a number for the intercept, we represent those letters a little different. So I'm actually going to, maybe I'll just cross this out. We use a different notation. It still has that general format of a line, because it's still a line, but we will call this y hat. It is the estimate of the y values. Usually the intercept is written first, and it's not just b, but b naught, or b with a 0. And the term with the slope multiplied by the explanatory or predictor variable. And this is just a sum, right? It's still mx plus b, it's just been written in the opposite orientation. So I'm going to label these portions here. This is the estimate of the y values, estim, or maybe we want to say the predicted y values based on the line, predicted or estimate. B naught is our intercept, y-intercept. B1 is our estimate of the slope, slope estimate. And I should also say this is our y-intercept estimate. And of course, x is our explanatory or predictor variable. Predictor slash explanatory variable. We're going to talk about some more elements regarding the least squares regression line here. For instance, how do we obtain these estimates for slope and intercept? And as a reminder, we are estimating these because this is based on sample data used to estimate the population slope or the population intercept. Let's start with estimating slope. I like to take an intuitive approach to this. There's really a lot of math that goes into these formulas, but if we have a scatter plot with, let's just say, a positive correlation, doesn't really matter, and linearly correlated, the least squares regression line would have a slope, in this case positive, rise over run. But how are we going to obtain the rise and the run elements from these coordinates, right? x1, y1, x2, y2, all the way up to xn, yn. Well, we would need the typical rise over the typical run, right? We need to consider those triangles that formulate the slope. Here, when we're working with data, it turns out that the slope can be estimated by the standard deviation in the y variable over the standard deviation of the x variable, multiplied by the correlation coefficient. So for every 1 unit change in the x variable, we would expect the y to change our standard deviations in the vertical direction. So it has a sensible formulation. Fun fact, the least squares regression line always goes through the coordinate, the mean of the x's, comma, the mean of the y's. So that's a point somewhere along the least squares regression line. If you know a point on the least squares line, then you can find the value for the intercept, right? If you know the slope and you know a coordinate, then you can solve for the intercept. The equation for the intercept estimate is the mean of the y's minus slope times the mean of the x's. Now, I think it's useful to have seen these formulas. However, we will mostly use R to compute these. The slope and the intercept estimates for the least squares regression line. And I'll show you how to do that shortly. But first, let's talk about another element of these components of the line, namely the hypothesis testing perspective. To discuss hypothesis testing in the context of linear regression, we need to discuss a little bit about the idea of modeling, particularly a linear model. Our line written above applies with sample data. However, that sample data is used to estimate the parameters that of the slope and intercept And here, the appropriate notation would actually be the mean y value for a particular x value, y given x. So this is almost like a subpopulation in which we're investigating the mean response given, or when you plug in a particular x value. We know that there is variability in these y values even for a particular x. So we often write the equation of the line, but this y value can vary depending on the x input. There is some error which represents the variation of our response variable. So I will write that. This is the random error, because we know y varies even with a fixed x, even with x fixed. So just for clarity purposes here, we know that B0 estimates, it's from a sample, right? It's the estimate of beta 0. B1 estimates beta 1, kind of much in the same way that y bar estimates mu, right? These are, on the left, these are our values from a sample stats, used to estimate the population parameter. Okay, so the hypothesis testing applicable for linear regression is actually all about the slope. So the hypothesis test investigates if there is a significant dependence of y on x. The null hypothesis, therefore, is about the slope beta 1, right? That's the parameter. And remember that we always use equals for the null hypothesis. And the null is always a statement that there is no effect or no change. So what value would indicate that there is no linear dependence between the two variables? Well, if the slope was 0, that's the value that would indicate that y does not depend on x. Therefore, the alternative hypothesis would just be that the slope is not 0. A couple notes regarding this hypothesis test is that the test on the slope, beta 1, is not a test about whether the relationship between x and y is linear. Actually, the test asks that under the assumption that the linear model is true, that we can conclude that the slope is not 0. So, like always with these hypothesis testing conclusions, the precise way that we state those conclusions is of importance, so that way we do not make claims regarding elements to which we have no claim to. So we're not testing if x and y follow a linear relationship, but just that their slope is not 0. And we can conclude a non-zero slope when we reject the null hypothesis, right? So when we obtain a p-value that is less than alpha. So how do we do the test? Well, of course, there is a test statistic. Of course, there is a p-value. How do we do all that? Well, we will use R, of course. Let's let R do all the number crunching. So I'm going to open R and use the example from the previous video. This was the CARS dataset that's preloaded into R, and we saw that the linear correlation coefficient is quite strong at about 0.80 or so. And we see that we should have a positive slope. So let's go find the slope and intercept estimates for the least squares regression line. All right, well, this is with the function called LM. That's for linear model. And the way that this is input, it's with y squiggle x. So I'll comment this out. This is the general format for the input for linear model. So you need to have your x and y variables, your predictor and your response pretty clear in your head, right? Because here, our y variable is the distance, and the x is the car's dollar speed. So y squiggle x. And what I like to do is give this a name. I'm going to call this model. And I will run our linear model there. As usual, we do not get any output from R when we give it a name. I'm going to ask for a summary of that model. And this is where we're going to get a lot of information in our console. Let's check it out. Okay, so a lot to look at here, but what we're going to focus on is the estimate. This is the estimate for the intercept right here, about negative 17.579. And the slope estimate is about 3.93. So this very first column here is of importance, and it does say intercept. And this one is indicative of the coefficient on our x variable. We do have standard errors and test statistics, but we're not going to compute those by hand. We'll let R do that. Over here is what we want to focus on, is the p-value for the slope. Here, the p-value is very, very small, indicating a significant non-zero slope. So I'm going to write some of this down. Since our p-value is very small, less than our usual alpha, then we would reject the null hypothesis, indicating that there is a significant non-zero slope between speed and distance traveled. It would be really cool to draw the line, the least squares line, on this graph. Well, because we created this model, we called it model, stored within the model is the estimates for the slope and the intercept. So kind of a nice little tool here is AB line. AB line will extract the slope and the intercept from our object called model, and it will place the line with that slope and intercept onto that image. And that's pretty fun. And if you like to play around with colors like I do, then maybe you can give that line, the AB line, a nice color. I'm going to choose red, and hopefully that looks like what you would expect. So I would like to make one more comment before we terminate this video, and this is about slope and its interpretation. Remember, slope is rise over run, and this is the estimate of rise over run, which is the change in y over the change in x. So I'll pose my comment in the terms of a question that will be sort of a fill in the blank. How much further do you expect to travel distance for every additional unit increase in speed? And that's, of course, based on the least squares regression line. So for every additional unit increase in speed based on the regression line, we expect to travel how much more or less? Well, every 1 unit increase, how much more? So it's definitely more. And how much more? So those little triangles, for every 1 additional unit in speed, we would rise how much? Oh, well, wouldn't it be 3.93 additional units of distance? So for every additional unit increase in speed, whatever those units were, based on this line, we'd expect to travel almost 4 units more, whatever those units were. So rise over run. We will stop this video here, but we will continue in the next video and talk about some diagnostics regarding this least squares line, including some of this other output from R down here.